Everybody knows that if you climb a tree, you probably cannot get down. You couldn't even find yourself. Okay, so a friend of yours, or maybe you, have climbed a tree to a height of 12 meters, about 36 feet. But you forgot, or he forgot, or she forgot, the bagged lunch, and they're very hungry. Now, you can't toss it straight up from below them because there's branches in the way. So instead, you throw the bag from a height of 1.2 meters, like from your shoulder, because you're throwing it, and a horizontal distance of 3.5 meters away from the tree to the location of your friend. But you want that bag to have zero vertical velocity whenever it reaches your friend. So it's just like floating there and they can just grab it, okay? So if that's the case, what must the horizontal and vertical velocity components of the throw be? So let's just draw a picture. Pictures are so helpful for problems like this. So here's the pick, there's the ground. Here's the only way I know how to draw a tree. Here's your friend in it. Maybe the tree is your friend, I don't know. Now you are down here. You're 3.5 meters away from the tree. You throw the bag from 1.2 meters off the ground, and your friend is up here in the tree 12 meters high. So what does this tell you? This tells you that your friend is really just a difference of 10.8 meters up, right? The whole tree is 12 and you're starting 1.2. Your friend's really 10.8 meters up. So what can we put into the box from this picture? Well, we know if you're throwing the bag 10.8 meters up, we know the bag's displacement in the vertical direction is a positive 10.8 meters. We also know the bag has to go to the right 3.5 meters, so that's the delta x in the x direction. What else do we know? We know that whenever the bag gets to your tree, we want it to have zero vertical velocity. So that means our final velocity in the y direction is going to be 0 meters per second. And what's causing it to slow down vertically? Well, that's gravity. That's negative 9.8 meters per second squared. Okay, cool. And what do we want? We want to know what are the horizontal and vertical components of the throw initially. So we want these initials for the horizontal and the vertical. So if we recall on our best friend, for our left side, whenever our acceleration is a 0, we need 2 out of the 3 things over here, being the velocity, delta x, and time. And if we're rocking the y side of things, we just need 3 out of 5 in order to use our best friend and figure out everything else. And we have 3, 1, 2, 3. So we've only got one thing on the left because the acceleration doesn't count, but we've got 3 on the right. So let's start on our right side, the vertical side, the y side, to solve for some stuff here. If we've been doing a bunch of these problems, maybe you're starting to recognize what's going to go down. Since I've got 3 things here, I could solve for VI, and that's half of our problem there. But on the left side, I need to get something over here, and what I'm going to end up doing is finding a time, transferring it, and now I'll have 1, 2 out of the 3 things, and I can solve for the VI here. So let's just solve time first, because I think solving for that time will allow us to get a maybe more straightforward value here. Or could we solve for time first? Is that even possible? Delta x, VF, and A. Delta x, VF. Ooh, that looks bad. I don't think we can solve for time first. Let's solve for the initial velocity first then. Taking a look at my equations here. It looks like we're solving for the initial velocity first. Or maybe I'm just not seeing something. Either way, we'll solve for the initial velocity first. So if we want this initial velocity, and we've got VF, delta x, and A, we don't have time. There's only one equation that does that. It's number 6. And equation number 6 is the final velocity squared equals the initial velocity squared plus 2 times the acceleration in the y direction, because we're on the y side, multiplied by the displacement in the y direction. So some people call that delta y instead of delta x, but it's a displacement. Who cares? So that's the only equation we can use. And at this point, it's just a matter of punching in numbers and solving for VI. So 0 squared is 0. This equals VI squared plus 2 times negative 9.8 times 10.8. And what's really nice about this is, wait a second. This looks funny. Why does this look so funny? Oh, it's going to look funny like this. Okay. Sorry, I had a brain fart. This is 0 equals vi squared plus, and let's multiply all these together, okay? The reason why this looked funny to me, I was looking at this negative number and I was like, wait a second, I'm going to have to take a square root in a second. I'm going to get a negative out of this. This is going to be bad. I'm going to get an imaginary number. But when we multiply this together, 2 times negative 9.8 times 10 is going to give me negative 196. And to solve for this VI, we're going to bounce the 196 over to the other side. That's adding it over, and that's what we want, because now we've got a positive 196 equals the initial velocity squared. And now when I take the square root, oh, I was worried there. Now when I take the square root, we'll find that our initial velocity is, what is this? 14. Ooh, perfect square. Meters per second. So we can go up to the box. We can say, hey, our initial velocity is 14 meters per second. We got that value. Half the problem's done. Now we can go down and get our time quantity here a little bit easier. So we can go solve that. We've got 4 things here. We can pretty much choose any equation we want. Let's go use equation number 3. I think that equation is arguably one of the easier ones on our best friend. If you're thinking about equation number 3 is that the final velocity equals the initial plus the acceleration multiplied by time. So put numbers in, we get 0 equals 14 plus negative 9.8 times t. Do a little bit of subtraction magic, pull the 14 over. So negative 14 equals negative 9.8 t. Divide by that 9.8. Divide by negative 9.8, both sides. Make the sound effects because it's awesome. We have the negatives that go away, which is great, because now our time will be positive. We haven't gone backwards. And whatever 14 divided by 9.8 is, 1.43. Our time is 1.43 seconds. Cool. So that's not actually what we want to find our answer, but because we now have this time of 1.43 seconds, we know that time has to link. So this is 1.43 seconds, and now I've got 2 out of my 3 things for the left side of the box. And on our left side of the box, we're always using equation 1, which is just that a velocity equals a displacement divided by time. Our displacement here is 3.5 meters. Our time is 1.43 seconds. So whenever we do that little division, 3.5 divided by 1.43, we simply get a velocity in the x direction equal to 2.45 meters per second. And that's it. And if we did throw it back up in the box, remember, it's not just the initial velocity, it is both of them, because there is nothing on our bagged lunch that is accelerating our lunch bag. There's not like a rocket booster, once it leaves your hand, it's just moving, it's just doing its thing. So that's both the initial and final velocity, and that's why the acceleration is 0. So with that was a little bit longer of a problem, but in the end, we kind of saw it was just more of the same old, same old. We drew a picture, just like old Grandpappy Botzer taught us to, okay? Even though a picture looks like garbage and your friend doesn't have a body, the picture allowed us to get a proper y displacement. We knew gravity. We knew that whenever that bag reached our friend, it wasn't going to be moving up anymore. It was like at the maximum height, so the final velocity was 0. And then it was just use your best friend to get an equation, use your best friend to get an equation, move that time over, use your best friend for an equation. And that's it. So a little bit of math here, but a lot of the work was originally just set up for us thinking about the physics and kind of drawing out that picture. So as long as you kind of follow those steps, you'll be fine with most of these problems. And this problem is finished. Our very last practice problem we're going to take a look at in this unit, it's actually going to be an optional challenge problem, 15.5. The reason being is that, what we've been looking at here is just a nice setup where, hey, we have these variables, let's put them into an equation, let's get an answer. What we're going to see in 15.5 is we're actually not going to have enough information initially, and then we're going to have to link some things together in order to solve out for that problem. Okay, so that's a challenge problem coming up. That'll be our next video. But until then, adios, and you all take it easy. Have a great one.